So here we go with question 6 from paper E. Particle P passes through a point A, velocity 2.8 meters per second with a constant acceleration of 0.12 meters per second squared. So let's just get that on a diagram. So here's our point A. It passes through with speed of 2.8 meters per second. And it's got an acceleration of 0.12 meters per second squared, and that's P. 3 seconds later, so if we call that at t equals 0, down here, this will be at t equals 3, Q. It passes through A with a velocity of 2.4 meters per second and acceleration of 0.2 meters per second squared. It doesn't say it in the question, but I've assumed there that it's travelling in the same direction and along the same straight line. Otherwise, the question doesn't really make much sense. Okay, so the key other word to pick up on in the question is constant acceleration. So that tells us, as soon as we read it, that we're working in a SUVAT kind of context. So let's now think about converting this. Write down an expression for the displacements of P and Q from A in terms of T, where T is the time after P passes through A. Well, as we've said, P is at A at T equals 0. That fits. Yeah, so after time P passes through A, so we've said T equals 0 there and T equals 3 for Q. Okay, to pass through A. So consider P. We want the position of P, so we'll call that SP. So we're going to use SUVAT. We want S, the displacement, so that's going to be S of P. The U is U of P, which is 2.8. The acceleration of P is 0.12. And T is the time since P passed A, so we'll just call that T. What equation do we use? So it's going to be S equals UT plus a half AT squared. And now we can substitute in SP equals 2.8T plus a half times 0.12 T squared. We can tidy that up, 2.8T plus 0.06 T squared. Okay, now we can consider Q. So S is equal to the position of Q, SQ. U of Q is equal to 2.4 meters per second. The acceleration of Q is 0.2. And T, this is where we have to be a little bit careful, because we were told here that at Q passes through the origin at T equals 3. So we need to say T is equal to T, the current time, T, and then take off 3. So when we put 3 in as 0, so therefore when T is equal to 3, S will equal 0. Therefore, at A as required. That's what we've had to do there to fix the position at T equals 3 as being at A. Okay. So now we can go SQ equals U 2.4, lots of T minus 3. I'm just going to move that across a bit because I'm running out of space. So I'm going to start here. SQ equals U, which is 2.4 lots of T, minus 3, because that's the time for Q, plus a half A, which is 0.2, T squared. So that's T minus 3 squared. Let's tidy that up. So we get 2.4T minus 7.2 plus 0.1 times, or we could expand that, T squared minus 6T plus 9. And again, we could improve that. So we get 0.1T squared. We've got minus 0.6, so it's going to be plus 1.8T. Negative 7.2 plus 0.9 is negative 0.63. So we've got expressions for P and Q in terms of T, where T is the time after P passed through A. Show that when the particles meet. So what's the condition for particles meeting? Part B. SP is equal to SQ. So we've got 2.8T plus 0.06T squared equals 0.1T squared plus 1.8T minus 0.63. Well, we've only got whole numbers in our answer that we're aiming at. Yeah, up here, everything is a whole number, isn't it? So let's get these into whole numbers. Hopefully, you can recognise the best way to do that is to multiply through by 100. So we get 280T plus 6T squared equals 10T squared plus 180T minus 63. That's worrying me. It's not 0.63 there, is it? It's 6.3. 9. Sorry. It's minus 6.3 because it's 7.2 minus 0 plus 0.9. So again down here, that's wrong. So that's going to be minus 6.3 still. So when we multiply by 100, that's 630. Okay. Now we want a positive quadratic equal to 0. So naught is 4T squared. Subtract the 280T. It gives minus 100T and minus 630. Well, we've got whole numbers now. Go back 2T squared. So divide through by 2. And we get naught equals 2T squared minus 50T minus 315. And let's have a look. Yes, we've got that right. Find the distance from A when the two particles meet. Okay, so we've got a quadratic. Looking at 630 and adding to give minus 50. I can't see anything that's going to work for that. So I think we better use the equation. Okay, so just remembering that that's A, minus 50 is B, minus 350 is C. We have to take the sign before the number. So T is equal to minus B plus or minus the square root of B squared minus 4AC all over 2A. Right, you really should show this line with it substituted in. So negative 50 plus or minus negative 50 squared minus 4a minus 315 for C, all over 2 lots of a, which is 2. So we get 50 plus or minus the square root of quite a big number, 2500 plus 8 times 315 is 2,400, 520. 2,520, I think. Anyway, we'll check it on a calculator. So we're going to tap it in the calculator in the end, so that will be over 4. You can check the number work, and I think that comes out to be T equals 30.21 or negative 5.21. Okay, so what do we find? Show that the particles meet, find the distance at which they meet. So we reject T equals negative 5.21 due to context. So now we've got to find the position at that time, and it doesn't matter which one we use. It seems to make sense to go back and use P. So from SP being equal to 2.8T plus 0.06T squared, if I've remembered that correctly. Let's just check. 0.06T squared, yes. So put it in the calculator, substitute in the 30.21. Best to use the answer button really, so you're going to be using 2.8 times 30.21, but use the answer button, plus 0.06 30.21 squared. So SP comes out to be around 140-ish. Let's just check it. 139.36 meters. That's a fairly excessive level of accuracy. If we go back, look at the question, nothing's given to more than one decimal. Oh no, the acceleration's got 2 dp, but nothing's given to more than 2 significant figures. So 2 sig figs of accuracy on the answer would give 140. You might put 140, you might go to 139 meters. I think the mark scheme says 139, but it's questionable whether that's a reasonable level of accuracy. Perhaps 140 would be better. Okay, hope that helps.